We are honored and delighted to have as keynote speaker to kick off today's proceedings given by Professor Jiawei Han from University of Illinois. He is Michael Aiken Chair Professor at the Civil School of Computing and Data Science at UIUC. And he's a world leader in AI, machine learning, artificial intelligence related topics, including data mining of text information. And he has published quite extensively in all kinds of prestigious journals throughout the world. And he's going to talk about embracing large language models for geospatial applications. And without further ado, I invite Professor Jiawei Han to come and give his talk.
Yes, thanks a lot. Good morning, everyone. Yeah, so for the talk, I basically just trying to link the large language model with geospatial applications. Of course, for geospatial application, what we have done is quite limited, but there's some promising direction we probably can discuss. Feel free, during the talk, if you got any questions you would like to raise hands or raise questions, feel free, we can discuss, even in the middle of the presentation, okay? So my talk mainly is starting with this retrieval augmented generation for large language model, just because we believe that's the future, especially for our concrete applications, okay? I think everybody has been playing, ChatGPT or whatever large language model you love, okay? And for our iGuide, we definitely want to embrace ChatGPT, those large language model. We can do something quite fancy. But people may experience, if you work on raise questions on some common sense, questions. Nowadays, especially you hook up the advanced GPT, like GPT-4o or something, you get very good answers. However, as a researcher, you want to go deep to solve your problems. Quite often you feel they are not sufficient. Sometimes they are overly confident, they hallucinate. Okay. Why that could be the case? Okay. If you think about it, when we do research, we want to go very deep and very current. Okay. But you go very deep, the large language model may treat your question as very, very specialized. They call long tail problems. So they may only skip the surface. They may not go that deep. Even they have billions of parameters, you could be out of these billions of parameters. Okay. Another thing is very current. In the sense, you want to ask a language to solve some problems. You just saw the paper in the last several weeks. They may not even know the paper. It's not in their training data. How they could answer? They don't have such a knowledge, right? So that's the problem. We want to see how we should handle, large language model with current deep knowledge for research. Okay. So what we propose is we need to go down to structure something to feed into large language model. Okay. I just give you one interesting example I myself experienced. Even we did it almost 2 years ago. Now it's 2025, in early 2023, when ChatGPT just came out. Okay. And NSF actually organized a workshop discussing. They invite about 50 people who were very good on AI, including language models. They want to discuss, what we should do, whether we can take the opportunity. In the meantime, we don't get into any disasters. Okay, they ask everybody give 5 minutes lightning talk at the NSF panel. Okay, so for preparing this, I actually asked my student to say, "You play with ChatGPT. I give you one query to see how it can answer." The query looks very simple. Just say, find a highly cited paper on heterogeneous information networks. Why I pick up the heterogeneous information network as a query? Just because we have done a lot of work. I just want to test whether they can find our paper. To our surprise, they find, we say, list top 5 or something. They find 5 papers, and every paper has my name there. Okay, so I was a little pleased. I try to see what they can find. To my surprise, none of the paper is real. Okay, I never wrote such paper. For example, I just give you this one example. The example said heterogeneous information networks and analysis and mining a comprehensive survey. It looks that tighter, it must be highly cited, but we never wrote such a survey. Plus, they say it's published in KDD. KDD research papers, they don't publish surveys, right? So that obviously is a lie, but they lie in a very confidently. They say by March 2023, they cited 4,300 times. We never wrote such thing, right? So then we realize actually this query looks very simple. There's no way they can answer it because citation was not part of the training data. If they really want to get a highly cited paper, they have to build a gigantic matrix like a Google Scholar. If they do not know, they have to call Google Scholar. There's no way they can solve it. Okay, so you probably can see there's some limitations for large language model. Okay, so then I got into a survey on retrieval augment generation. They basically give this very nice figure, but I put 2 stars there. Okay, the figure basically say, if you really want large language model to work on your domain, your problems, you have to look at the x-axis and y-axis. What is x-axis? That means you go further and further, you have to do fine-tuning. That means your current domain may not fit the already trained. You have to somehow retrain them, okay? That's why a lot of people ask lots of GPUs because they want to retrain it, they want to fine-tune it, okay? But another one is you try to use smart way to prompt the large language model, because the large language model has lots of knowledge buried inside, but they do not know how to get it out. You have to write a very smart prompt. They call prompt engineering, like chain of thought, tree of thought, those kind of things. However, no matter how you nicely try to prompt them, if the knowledge was not there, there's no way you can prompt that out. Then how you do it? You add additional knowledge. The y-axis basically say, add external knowledge more and more and structure it, okay? The structure them is what we added. We say, not only you need to add those things, retrieve the related knowledge, but you also need to structure them somehow. Then you can get it out. So get 2 stars, 1 stars without fine tuning. You structure them, retrieve them, then you can work together with large language model. The red star, the purple star actually says not only you need to get knowledge, structure them, but you also need to tune them. Okay, that's especially we're working on, for example, the big chemistry things. They are very specialized. You add a lot of domain knowledge, you tune the model, you get a new model, then you can still do retrieval and structuring. Okay, so that's the roadmap. With such roadmap, we basically say, if we want to solve the problem, we need to go this way. Okay, this way means this roadmap says you get the knowledge from the papers, from map, from all these, and you get knowledge from Wikipedia or those knowledge bases. And you also got something like in using some large language model, you can do retrieval to get things you need. And in the meantime, these retrieved things need to build knowledge graphs or build some structures. Using such knowledge, you feed into large language model. Likely the large language model will give you something very, very sharp. Okay, so that's the framework. You probably see sometimes you even need to go back to feed them, because when you find your retrieve or structure things is not good enough, you want to feed back to solve the problem. So that's the basic, framework my group has been working on. Okay. So let's first discuss how to do retrieval, and then how to do structuring, then how to solve real problems. Okay. So for retrieval, there are many, many things. The very important thing is, in the past, if you look at a Google retrieval, of course, Google is still evolving. They get a lot of new ones with large language model. Before large language model, the Google retrieval basically doing two things. One is using, they call the keyword-based, inverted index-based, or people just say TF-IDF or BM25 using those keywords to do it, okay? Another one is they base on massive weblogs, the search history, including human feedback. They build, they call deep passage retrieval, okay? Then they can do it. But that one did not involve large language models, okay? The newer one, actually, this is one of the papers we just submitted, still currently under evaluation. But very interestingly, this student proposed this deep retrieval, currently is doing summer intern in Google search, okay? And he actually last night sent me an email, said what we did, the theme-based, theme-focused search is exactly Google currently is working on, okay? And he actually said what he did, this is very much related to what Google currently is doing. Summer intern is working on this. What he did, this deep retrieval is, he has some training data, but he wants to use the training data in a very, very nice way. How nice it is he kick in those reinforcement learning. Simply says, you give me a query, okay, suppose this is just try to tune your model or try to, train this. How do you train it? Is you first use the search engine to get some results, okay? With this results, you have some training data. You actually take this training data and say, whether this results based on my matching is a good match, is off touch. If it's good match, this is positive training data. If it's mismatch or it's not what I want, it's a negative data. And he basically takes the positive and negative data, turning this into reinforcement learning. That simply says, I actually do not need you to give me training data, but I use this back and forth. We actually feedback to tune my search engine, okay? In that way, with the limited data, he can get very good, results. What's the results you can see? He actually compare with many large language models, like here, and with some, search engine as well. You actually can see, finally, he got very good results. He actually tried his method comparing with, if you look at this, this is a GPT-4o. Yeah, this is like Haku GPT 3.5. Now, all these comparing to his retrieval, the results. The blue one is on, these two are two. One is on the search for the patients, for the PubMed. The other one is on the research publications. Both of them, you get really high results. Simply say you get much higher recall compared to the current large language models, okay? So that's the one you can do reinforcement learning to enhance it, okay? But Today, I'm going to introduce actually Jiawei Shi. Jiawei actually working together, with Hypercube rack team. Okay, I'm going to introduce. This is very much related to geospatial because all the examples are geospatial. Okay, but it shows it's very powerful. Okay, what does this mean? Okay. Remember how the current researcher is trying to get good search engine. Okay, one way, like in Microsoft, they invented one called Graph Rack. What does Graph Rack mean? The Graph Rack basically say, you give me a search query, based on this query, I try to build a graph. Okay, but in my documents, I also have a graph. Okay, I want to see your query graph and document graph have a good match. This one is a good subgraph of your whole documents. I'll grab it out. Okay, that looks very good. But you think about this. There are so many entities and links. The graph will be gigantic. To construct such a graph is very expensive. Matching is also very expensive. Okay. Now, Jiawei, based on this, the HyperRack team, based on the Hypercube. What does Hypercube mean? Okay, Hypercube means when you have lots of documents, you try to classify, arrange these documents in a multi-dimensional space. Okay, just think about this particular one, like Florida, you get a hurricane, you get tropic storm. You arrange this into 3 dimensions. Okay, the 3 dimension, one is on location. Okay, you go down to Florida, you may have a concrete location like a Melbourne Beach, Miami, downtown Palm Beach. You get all these different locations, but you also have an event like different storms, like Tropic Storm Faye. Okay, you can link in this way, but you also have a theme. Theme may be related to weather, related to heat or rain, climate or earthquake or hurricane. And with this, you get different themes. These 3 dimensions, you just think about it. You get a document. If this document is about a particular location, particular event, like this, tropic storm Faye, you base on this, you actually can locate where the document should be in. Okay. Remember, this one is you ignore very detailed. People, when they write documents, they may mention many things. You ignore a lot of detailed things, but you focus on a few key dimensions. Then you locate your document very quickly, unambiguously, in a very efficient way. That can help you to find the right documents, isolate the right documents. You feed into large language model, they're going to tell you something quite smartly, okay? So that's the general philosophy. And with this philosophy, actually, we did some experiments on this. You probably can see, if you get the documents, for each documents, you try to find, those different dimensions, you put them in the right place. When you get different queries, you actually can see whether they have a very good match to exactly things you want to fetch. Okay, so actually for this dimension, you actually can see there are several, like you have 844 documents, you match to 300 QA pairs. Simply says your documents and your question answering pair may have very good match using this cube structure. Okay. And with such cube structure, you actually can see, if you like to know more, tomorrow I have about 10, 15 minutes. I will introduce Jiawei's paper in many details, okay? But in this one, I basically show comparing to many other methods, okay? There are many RAG, they call retrieval augment generation methods. But this cube method, the first interesting is the retrieval quality. No matter you use hurricane, geography, or aging dam, the quality, the very last, the bold one, is compared to many other methods, your retrieval quality, no matter you start from the general metric, like a bird score, like a blue, those kind of metric. Bird score means using bird, you see the query and documents as a very good match, okay? And if you use LLM as a judge, simply says, you use multiple LLM, say which answer is better, okay? That's take a collection of LLM to judge it. No matter what, you can see the quality actually is very high, okay? Not only the quality is high, but also the method is very efficient, okay? The quality, you actually can see this one is using different methods. No matter you use GPT-4o, DeepSeek R1, QN 2.5, and Llama 3.3, and this hypercube method, which is a green one, is always higher. Okay? That means independent of large language model, you get better results. But more interestingly, you look at this figure, okay? Like GraphRag, which I just mentioned, Microsoft actually invented this GraphRag just a year ago, okay? But if you look at the efficiency, okay, you probably can see this one is in the microseconds, but milliseconds. The milliseconds, remember, actually, I got one student, she, after getting PhD, she joined Google search team. And she actually told me, Google want you develop any AI package, you want a Google search engine to take it, to really have search. They first measure how efficient it is. And their measure is in milliseconds. If you go above a dozen of milliseconds, they will throw your software away. The reason is very obvious, because your search package is just a part of the whole Google search engine. You cannot go over 20 milliseconds. The user at that end will think it takes seconds because there are so many overhead. They will think that your Google search engine hang there. Okay, they will not allow you to take more than 20 milliseconds. So if you look at this milliseconds, you probably can see the difference, because the GraphRag, if you get 14 times of the test set, you get 45,000 milliseconds. Okay, nobody wants to use your search engine. But you look at it, like Gmon, this hypercube RAG get 22 milliseconds. You probably can see that's, dramatic difference, okay? So that's why not only you get a good, but you also get very efficient. That's about search. What about structuring? That means when you search, you get it, you still want to structure it, okay? How to structure it? The very important thing is you want to turn your unstructured text into structured knowledge like table, okay? But if you say, I need lots of training data, people nowadays will not take it. Who wants to give you so much annotated data for you to train, especially in the new domain, right? So can we get this without training? We finally can get a table, okay? So actually my student, Yizhu Jiao, 2 years ago, she was using, that time the GPT was not out yet. She was using BERT, essentially, BERT-like language. But she basically showed, if you go through this whole framework, you get those earthquake reports, you get a bunch of reports, you based on this, you go to this BERT search engine, you can grab what are the roles or attributes. And going back using different prompts, you actually will grab the values, properties out. So you get both roles and arguments. You can extract them automatically using small language model. Okay, the result actually is very good. And the prompts is very simple. If you see those marked yellow ones are just prompts. Okay, the prompts you go inside, actually those prompts will give you very good rows and arguments, and you will get very good results as well. So with the large language model, currently we actually working with IBM people working on this extract the material science, those different tables like this. And we get very good results with large language model as well, okay? So with this, we actually working on, we call reaction miner. What reaction miner is doing, besides being working with Xiaowen, with our team, working on this geography, geospatial data, I actually also working with chemistry, called Chemistry AI Center at UIC. The Chemistry AI Center, what they want is you give me the chemistry literature, sorry. You give me the chemistry literature here. I use PDF to text. And using this text, I actually go through this text segmentation using large language model, extract those using llama, using those things. You extract the structures, okay, like this. That means from the documents people writing, you actually can extract the tables and values automatically. And this whole thing called reaction miner. That means you can mine chemical reaction, okay? And you can put them into a table. You can even feed this into the experimental robots, okay? So it's a very automated, from the paper to robots experiments. You can just sleep there, but they are going to do it, okay? So this is pretty magic, but actually the accuracy is pretty high. And we just heard news last week, NSF even facing such a heavy budget cut, they finally granted this phase 2 another 5 years money. You probably see the NSF really made decision to invest on this chemistry AI. Okay, so that's actually the detail I'm not going to get in, but I'm going to show you some very interesting one. This year we just get 2 papers. One paper just published in iClear is very exciting. That's why I want to show it, okay? What's the exciting thing? The exciting thing is this, okay? You get lots of health care record, okay? EHR, electronic health record, okay? Can we, based on these health record for this particular patient, can we predict the outcome of the patient? Actually, of course, the outcome is not typical outcome. We got actually 2 outcomes we want to judge. Those are pretty heavy, you know, like serious patients. We basically, one is predict within or before the next visit time, okay, whether this patient will pass away. We call mortality ratio prediction, okay. Another one is whether this patient will be readmitted to the hospital, okay? So of course, those are very serious patients. But the interesting thing is they collect lots of data. Of course, it's fully anonymized, but they just say whether you want to use GPT, use those large language model to make a good prediction, okay? Of course, nobody wants to just feed in the patient record, the GPT will give you, you know, the person will die or something. That's pretty risky. Nobody wants to trust it. So there are lots of different methods working on the same thousands of patient record is competing which method can give you really good prediction because they have the labor data hiding, you know, but you based on the current training data, you have to get it, okay? But the interesting thing is not everything is like a health record, some disease in the table or some medication is in the table. It's not that, okay? Because you probably know the doctors writing in English, right? Everything is natural language, but they do insert those medication, you know, your situation inside those language, okay? With this, whether it can give good prediction, okay? What you probably can see is you use large language model, but we got like 4 stages. We finally can do really good prediction. What's the 4 stages? The first one is you take, if you look at this part, is you take the known knowledge, Wikipedia, large corpus about a medical and AI, the large language model. Working together, you can build a good knowledge graph for your domain. Okay. Then you take the patients, you get lots of patients. For patient self, you based on their writing, the doctor's writing and patient's health record, you build a patient knowledge graph. Now you have a medical knowledge graph, you have patient knowledge graph, you train these knowledge graph together. Okay. Finally, you can build a model which is very powerful in the sense you really based on the past history, the current patient record, lots of similar patients, you form clusters, you build knowledge graph, and finally you can do really good prediction, okay? And the detail how to use, how to use prompts and this to get information, to get training, how to use the medical record, you do this training. There are lots of details, I will ignore it. But I probably want to show you the final results. If you look at this, you actually can see there are thousands of training data. You can see this is the one training, mortality training. And for mortality training, these are number of patients. This is training data, 7,000. And the testing data is about 1,000. Validation data about 1,000, test data is 1,000. But for each patient, you get lots of visits and lots of medication, lots of different products, different things. You get lots of data. And with such data, you train it, you finally can see, this is just on one test data, this is on mortality. You can see there's so many in the past, there's so many machine learning methods plus large language models. And finally, you can see you use knowledge graph, construct the medical expert knowledge graph, compare the patient cluster knowledge graph. You finally can get a really, really high, you get the highest one. For example, on the mortality prediction, the accuracy, you actually can see you can get 95% accuracy. Compared to others, of course, there are some using large language model can get 94. Okay, but you probably can see you really can get something at the expert level. Okay, and this result we put it on the archive before it was accepted. The UCLA Medical School dropped me an email and said they found this paper. They want me to just give them a Zoom talk to their medical school students, 1 hour, just to explain this paper. Actually spent about 1 hour to explain this, how the whole thing works. And they actually got because it's open source, they get everything. They just try to, they are more in the cardiology. This is more like a cancer or something. So they work on the cardiology, try to do the prediction, okay? So another interesting thing, the last thing I want to show you, this one is just in the archive, but just submitted, okay? Currently it's still under evaluation, okay? This one is about how we can build causal relationship to explain what things happening, okay, in a very concise, very, very sensible way, okay? We actually took 2 examples to show the large language model, if you build a structure, it could be very powerful. One is, you probably know, called Bitcoin price. After Trump got elected, the Bitcoin get lots of fluctuation and it shoots up very, very quickly, okay? And what we want to see is how could you explain the recent Bitcoin, fluctuation and boosting up, okay? If you ask a GPT, any GPT, they were trained before actually the election results. They will not be able to answer it at all because they don't know it, okay? But that's what RAG can play the role. RAG will feed the new documents, new news document into it. Then they will be able to explain, but they explain it in a clumsy way if you do not actually build the structures, okay? And another one is Gaucher disease, which is a specialized disease, and you want to explain the whole thing. Okay. To explain this, in the past, people just use, say, GPT-4 or whatever new GPT or large language model you can get, you just explain it. Actually, we found this is not sufficient. What you need is build a causal chain. What you need is you take those relevant documents. Based on these relevant documents, you use large or small language model. You try to get this one A leads to B, or B was caused by A. You, based on these causal relationship, you build the chain structures, okay? With such chain structure, you use embedding, you can link those chains when the query comes, and it becomes very powerful, okay? Let's show you the whole process. The key is you try to grab three things: cause, relation, and effect. That means if A causes B, or A leads to B, or A, because of A you get, because of A you get B, or something, whatever you say in natural language, you grab this sentence or this passage, the large language model can easily figure out the causal relationship. Then they can get a cause, relation, and effect extracted. With such extraction, you actually extract almost hundreds of them. But you, based on what your query is, you actually can link this chain using backward or forward chaining. Okay. Once you chain them together, it becomes very powerful. Okay. So basically, we, based on user query, we extract the documents, the phrases, and the sentences. You build those causal relationships. With the causal relationship, okay, you actually can extract it. The interesting thing is you say, oh, what about we ask a domain expert to build? Domain expert is very expensive, but they do not know your query. You can ask anything. But the domain expert, for example, for this text, the domain expert extract those triples. That's causal effects, okay? And our softwares for CC RAG, the chain RAG, okay? This CC means causal chain. Using this causal chain, we extract for the same passage, we extract many more. But only some of them is related to your query. But when the query comes, we quickly identify which are the forward chain or backward chain. We can chain them together. And the domain expert extracted two scattered ones. They cannot answer. They finally say the causal context is insufficient to answer this question. That means you just use the domain expert. Domain expert is expensive, but they don't want to extract too many. Okay. But finally, you give a query, a tricky query. They just cannot chain them together. Okay. But if we get many such causal effect, you give me a query, I can automatically form a chain, and this chain feed into GPT, you can generate very good answers. Okay. So you'll probably see we took this two examples. One is Bitcoin price, another is Gaucher disease. And you see we using the retrieval get 20 documents. Taking the 20 documents, we get lots of triples. And take those triples, we actually can get a very good results. The results, one interesting thing you can see is if you get no matter using which GPT or Llama, we actually using bird score or some conciseness, we get much better answer than other methods, the simple RAG or zero-shot one. But if you use human to judge, this is LLM as a judge or human evaluation, our method is far better than the others. You actually can see this is zero. Zero means they just cannot answer. This is about a dynamic big, the Bitcoin, because you don't have the knowledge, but once you put a RAG, they are not, they are not zero. Like this one, it's get a rag, you get something, but you get a 1 or something. But this is still far weaker than what you explicitly extract the causal chain. You link them together, become much more powerful. Okay, so that's basically the very last one I want to show. There are lots of examples, very tricky query, but we show actually we can answer something very short. You feed into ChatGPT, ChatGPT can give you so long answer. But if you look at the CC RAG, give you the answer, is as good or even more, even clearer comparing with this very big answer by GPT-4. That simply says, if you capture the essence using this causal chain, you actually can capture the very essential thing. You feed into any large language model, they give you a very good answer. But if you blindly feed the thing into GPT, GPT can answer it, but the answer is so long, you finally find it's essentially the same thing. Okay, so that's the reasoning we show that the causal relationship you can extract, that you can be much more powerful than the large language model. Okay, so and finally, I should say is, if we want to do geospatial application, like we showed, that's hypercube rack, but there are many more things you can do. The general philosophy is we need retrieval, get the exact things we need to feed in. We need structure and structure them like into causal chain, into knowledge graphs. Then we need large language model, but we do not need them blindly. We need some structure to help large language model. They will give us really, really good solutions. Okay. So finally, I just show you a bunch of papers. You probably realize all these papers 2025 simply says what I showed today largely is just a very new work. Okay. Besides, there's one iClear already accepted. All the other papers still under evaluation, but it shows that the domain is very dynamic. Okay, you probably see. I look at like this year's like ICML or something. We got like when we look at the number of the submission, it's over 20,000. Okay, we get like 24 something. It's like at least 25,000 papers submit to one conference to review. It's crazy time, but I think it's a very exciting time. Thank you. Yeah, okay, thank you. And otherwise, yes.
Thank you very much for an excellent presentation here. I'm sure it has provoked a lot of interest, and there are probably several questions from the audience. So please, I'm going to start with the person in the back. So my question is, this is the mic.
Yeah, regarding the causality, we are economists and we are deeply concerned about all of these. And can we train the language models about the problems of correlation versus causality, and any statistical issues that can happen if we just take the correlation, or other types of issues that we had? How difficult would it be to include that to improve the possible to avoid those mistakes that could happen?
Yeah, this is a very good question. You'll probably see, even for large language model, if you go to large language community, they basically say in the past, okay, they did not pay too much on reasoning. Nowadays, the newer large language model, they use reinforcement learning, especially R1 model or some newer models. They pay a lot of attention on reasoning. They try to get good reasoning. Okay, but what here we show is, people can ask any kind of queries. It's pretty tricky. even for human, you think about your reasoning, you have to find a very good way to link all those different things together, okay? And to find this, the best way is you focus on each one, say, this one here to here, A to B, B to C, is kind of reasoning. But remember, you A to B, B can go almost many, many places. You want to chain them together, you need to find the primitives. That's what we got this causal triples. No matter it's triple or n-tuple, you need some primitives to clearly see that these things lead to this part, but this part, based on your query, are linked to someone. Okay, these primitives can give you very highly, structured reasoning graph. If you think about a human, how to do reasoning, especially when you get into like the high school, people doing those, geometry problem, you actually can see there are so many different theorems, but you actually can finally find the way to chain the right thing together. You need very, very good smartness. Okay, that's not, once you get a multi-hop, many ways to chain. Not every large language model, just based on natural language, you can chain them so nicely. You need to grab the key things, the key cause effect, how things can really chain them together, get a good reasoning. That's a part we believe. We get everything actually from large language model, but we do it step by step in a structured way. Okay, and some large language model just thinking, I get more parameter, more power feed into more electricity, I finally can solve it. We actually believe you need good structures, like human, right? Thank you.
Thank you so much for a very interesting paper. I learned a lot, but I still have a lot more to learn.
Thank you.
With respect to hypercube, you made a very interesting case with the hurricanes, but it's only three-dimensional. And I assume that's 3 dimensions because it's easy to convey 3 dimensions, but I assume it can be multidimensional.
Yes.
It's just, you chose that because of the way you can convey that. So that was multidimensional is possible.
Yes.
I have one other question, and this might demonstrate my ignorance of what you were saying. When you fine tune the models, how do you know you're not throwing out a relationship that was unseen before? When you look at the data, you say, oh, that's ridiculous. The example I have in my mind from my personal experience was when the British were taking measurements in Antarctica about the ozone, they kept throwing out the readings they were getting because they said that's ridiculous. And it was finally, after a while, they realized that this is not ridiculous. It's actually something going on. Whether that particular story relates to your fine tuning, I don't know, but that's my question.
Yes, that's a very, very good question. Okay, the first thing is the hypercube. Definitely hypercube by nature is multi-dimension, is high dimensional. What we show here is just like a cube because it's easy for human to visualize 2D or 3D. You get a 5 or 10Ds, it's hard to even put it on the paper, right? So, but in practice, it is more dimension, okay? Usually 5 to 10 dimensions is very typical. But even those dimensions, the key is you don't treat every phrase, everything as a dimension. The reason is that once you get too many dimensions, even human, okay, you think about problem solving. It may not be that effective, right? So, okay. So with this, what we say is this beauty of this hypercube is extract a few dimensions humans think are most important. In the sense, it's kind of a human intelligence integrate or, interact with the large language model. Because the large language model, if you look at the Microsoft, this graph rack, they basically take almost any meaningful phrases as one node, then you can link to anything. Actually, Jimeng shows there some meaningful one, like for a hurricane, you get like a near normal or above normal or below normal. These are all meaningful, but actually it's not necessarily below normal must be hurricane. It could be other things, right? So with this, you try to chain those things together. Actually, sometimes is a little beyond your reasoning intention. Okay, so you grab the most essential one by human design this cube. Essentially, is you capture human design, capture the key things you want, put those documents together. Okay, that's the reason. Of course, we are studying. Sometimes you need multiple cubes working together because you can branch very far. Okay, to something. So we are still studying this, get a multiple hypercubes, how link them together, solve one problem, one complicated problem, which is very good. Thank you.
Thank you, Professor.
Yes.
We have to move on in the interest of time because we are running a bit late already. Thank you for an excellent talk.
Thank you.